In this video, I want to look at the exponent rules in a group where the group operation is written multiplicatively. Our author states the following theorem, and I encourage you to stop the video and copy this down in your notes for yourself and think about what it says, because it's too many symbols for me to actually try and read to you. So hopefully you've stopped the video and you've copied this down in your notes and you've actually taken the time to read what this particular theorem says. It's important to realize that these first two properties are very familiar. They are the same rules that you know about for exponents inside the set of real numbers. The third property may strike you as weird, and that is okay. By the end of this video and the next one, that will be fully explained. It's important to realize that when we're trying to prove this theorem, that if m and n are both positive integers, this expression here just represents a certain number of copies of g written over and over and over, and in fact it will wind up representing m plus n copies. And the same kind of thing applies here. In other words, the proof of this theorem when n and m are both positive is actually very easy. The more difficult part of the proof is how do we handle proving these formulas work if one or both of n and m are negative. And in order to do that, we have to prove the following lemma. So my lemma is going to be this. We're going to let G be a group. And we're going to assume that the operation is written multiplicatively. We're going to let little g be any element of that group G. And we're going to let n be a positive integer. Then it turns out that g to the n's inverse element is going to be equal to the inverse element of g raised to the n. And the way I want to prove this lemma is I actually want to do an induction proof, primarily because I want to review how to do an induction proof. And this is as good of a proof as any for doing that basic review. So our proof is going to be induction on n. Whenever you're writing an induction proof, it's worth letting your reader know that you are doing induction and what you're doing induction on. It's always important to write out the base step, and I would say write it out explicitly. We have to prove what goes on when n is equal to 1. Well, g to the 1 is just another name for g, and g inverse to the 1 is just another name for g inverse. And we already know that g times g inverse is equal to e, and so consequently we know that g to the 1 times g inverse to the 1 is equal to e, and that does mean that g to the 1's inverse is equal to g inverse to the 1. In other words, our formula holds when n is equal to 1. We now need to do the induction step. Now, when I'm doing an induction step, I always take the time to write down my induction hypothesis carefully. We are going to suppose that g to the k's inverse is equal to g inverse to the k for some particular value of k that is bigger than or equal to 1. I also typically take the time to write down what my induction goal is. I need to show that g to the k plus 1's inverse is equal to g inverse raised to the k plus 1. And now what I want you to do is I want you to look at this argument. if we have g to the k plus 1 times g inverse to the k plus 1, what we are looking at is g times g times g times g, where there are k plus 1 g's, and then we've got g inverse, all the way up to g inverse, and we have k plus 1 copies of g inverse here. And what I'm going to do is I'm going to reassociate the parentheses. I'm going to put parentheses there, and I'm going to put parentheses here, and I'm going to put a set of parentheses here. Now, when I do that, what I notice is I've got g times g times g, and there are now k copies of g times a nice big fat E, because this guy here is E by the definition of G inverse. And then we've got G inverse all the way up to G inverse, and there are K copies of G inverse there. And so what I now have is something that says I've got g to the k times g inverse to the k, and this is because E is my identity element. And so he drops out of that equation. But this particular product is equal to E by the induction hypothesis. That's where my induction hypothesis kicked in, and I want to stress that by going back and reminding you that the induction hypothesis is this step here, and that is exactly what we use when we go from here to here. So what I know now is I know that g to the k plus 1 times g inverse to the k plus 1 is equal to the identity element. And so, by the uniqueness of inverses, we now know that gk plus 1's inverse must be g inverse to the k plus 1. And that ends the proof of our lemma. And it's important to understand that this lemma gives us the following notational convention. When k is a positive integer, g to the minus k means g to the k's inverse, but it can also be interpreted as g inverse raised to the k.